So the first thing, I'm now on chapter 7. It's the work energy theorem, kinetic energy, and the work bias spring. And oh my gosh, I am so happy that we are now moving beyond kinematics and Newton's second law. What you're going to find here is that the way physics is done is not really done in the way that we've been doing things. And so what you're seeing here is what I'm saying here is that there's a paradigm shift. There's a big paradigm shift. And what I mean by this here is that problems can only be solved with constant forces. So when I look at this, problems can only be solved for when we're talking about motion and N2L setups. You can only do that. Otherwise, you are required to solve second order differential equations, which you cannot. Where problems with non-constant forces are not possible in this course. But the problem is, this is a very normal thing in real life. So a very simple example would be a spring. You cannot solve equations that have a spring in them. A spring force is not equal to a constant. It's a variable force. So that's one big paradigm shift. You can't solve problems with non-constant forces. And so what happens here is that work and energy concepts allow one to solve non-constant force problems. But there's a huge shift in thinking. And what you're going to see here is that work and energy is a systemic approach, whereas motion and Newton's second law, it's not about the system, right? So this is not about a system. And what you're going to find here is that work and energy is all about the system. So it becomes really, really important to really change how you view the world, right? Work and energy is all about the systems, and systems use conservation. Oh, how am I spelling conservation? Conservation laws to answer physics problems. All higher level physics is done with conservation laws. And what I really, really mean to this here is that I have a system. Let's say that this is my system. Some arbitrary system, A system could be a suitcase. It could be your car. It could be anything. And when we look at this system approach here, what you're going to find here is that work does something. So a systemic parameter is energy. And so what you're going to find in here is that you're going to do this type of thing. What happens here is that we either put things into the system. So if I'm looking at this thing, something is going into the system. Or I could have things that are coming out of the system. And as we track what goes in, what goes out, what happens here is that in the end, what we know here is that this system now, so when I think about the system, all we know is that the system overall does not change, but details about within the system do change. And this idea is immensely, immensely powerful. I cannot stress to you enough how important this is. It's a huge shift in thinking, and it's more comforting to think in this way once you figure it out. So what you're going to see here in chapters 7 and 8, we're moving towards conservation of energy. Conservation of energy, one of the most important laws in all of science. And then we get to chapter 9. And what are we going to deal with? Conservation of what? Linear momentum. Another immensely important law. And then we get into chapter 10, which is an outrageously long chapter, almost like 6 here. And what you're going to find here is that we get conservation of total energy. And what I mean by total energy is because now it deals with rotations, because anything that we talked about up to now cannot roll. If things roll, that's a major problem. This shit doesn't work. You have to modify it. And then we get conservation of angular momentum, which is, again, it's actually different than linear momentum, because now we have to worry about, again, rotational systems. And so these 3 laws, conservation of energy, conservation of linear momentum, conservation of angular momentum, these laws are the cornerstone of your intuition. Without these 3 laws, I mean, in fact, I'd go as strong as to say they're the first 3 commandments of physics. They're that powerful, that powerful. And all of these 3 laws plus Newton's second law for rotations gives you exam 2. Okay, so that's what our goal is here. So I'm telling you exactly what's going to be on the exam. One problem is going to be conservation of energy, conservation of linear momentum, conservation of angular momentum, and Newton's second law for rotations. So here we go. So what I want to do here is that I now want to start off with the first chapter, which I already wrote up above, but it's going to be on the work energy theorem. Which definitely is the way you think. If you say you think in the word of energy, you think in the work energy theorem. I'm pretty confident that's the case. And then we're going to get into the concept of kinetic energy. And then finally, we get into the work done by a spring. So here we go. So what I want to do here is that I want to give you just a very, very brief explanation of what work is, and that's what we'll start off here. Because in order to really understand energy, you have to talk about work. There's such a deep connection between these two. And what I'm saying here is that we all can think of work in some shape or form. So when we talk about doing work, what does one mean? Well, there's lots of ways to do work. Right? You could imagine carrying a box, I guess, right? So you could imagine that you have a box that you got to carry. So you'll probably, maybe the box is real heavy. And you're holding this box and it's real heavy. Wow, that neck's really bent quite a bit there here. Maybe not so bent here. And then you could imagine this person is stooped over because that's a very, very, very heavy box. And what we typically think about when we do work here, we're imagining that we're going to take this box and put it someplace, right? We're going to work to move this. And we're going to come over here and we're going to put the box, let's say right here on this table right here. And when you're doing that, what are you actually doing? You're applying some force and you're doing it over some, not distance, but displacement. So there's two important things that work is going to depend on. So work depends on, one, the force applied, and the displacement, not the distance, the displacement. The displacement becomes super, super, super important here. So let's go look at what I would say is a reasonable definition of what we mean by this here. So when I look at this thing here, what do I see here? Well, what I see here is that when I look at a good definition of work, there has to be two key components to the work. So, and this is what I mean. Where's my mouse? Here it is. So what I'm saying here is that now here's the definition of work. And what I'm saying here is that there are two key components to work. So the first thing here is that, so the work done by a force is, well, it has to be, we'll define work by the symbol W, and it turns out to be the line integral, not just the ordinary integral, it's a line integral. And the line integral is the force, and then there's a dot here. And what you're seeing here is that this is really a form of vector multiplication. And this vector multiplication, because we're dealing with real vectors, that means not pseudo vectors. You can't multiply pseudo vectors with the dot product, but we use something called the dot product. And what the dot product does is it essentially looks at projections of one vector onto the other, which we will talk about. And this here, by definition, is the area under the force versus displacement curve. And so what I mean by this here is that let's pick one particular direction. So if I pick one particular direction, let's say that I'm looking at f of x and x. Now, I could have a complicated curve. I don't know what the force is. And so what I do here is that I know that I'm starting right here, and I know I'm going to end right here. So it turns out that this shaded area, that is exactly equivalent to the work done by a force. So that is the precise definition of work right there. But there's another piece to the work here. And this really involves the work energy theorem, but I think it's important to start talking about it as soon as possible. And I think this is where the paradigm shift occurs here. In order to do work, the force must be either parallel / anti-parallel to the displacement. And these guys have meaning. So how do I define parallel or anti-parallel? Well, it turns out that there are three cases. So there are three possibilities. So what are the three possibilities? Well, one, I can have a force in this direction. And then I'm going to look at my displacement. Let's say that my displacement is in the same direction like this. And what you're seeing here is that if I have the situation, what we say here is that this is positive work. And positive work, of course, means that this must be the case. When you have a positive work situation, what you do here is that you increase something in the system. You increase something in the system here. And the key word is this guy right here. What is this something? It's called energy. Okay? That something is what we call, you know, the you increase energy in the system. That's what happens if you do positive work. Now, on the other hand, what if you have the opposite situation? What if you have a force going like this and the displacement is in the opposite direction? So in this case, you don't have positive work, you do negative work. And negative work, of course, means that the work is negative, less than zero. So this does what? It decreases energy in the system. Okay? Okay, well, I'm not trying them. I'm going to get. I'm talking about. So then there's a third case here. In this scenario here, what you're finding here is that the force can be perpendicular to the displacement also. And when that is the case, then here, what we call this is zero work. And what do I mean by work? It means that there is no change in energy for the system. And our whole goal in this chapter here is to really nail two down. So I would say that this is a precise definition of work because it includes what does it mean to be positive, negative, and zero work. And I'll tell you, one of the trickiest ones, believe it or not, is zero work. Okay, so let's go look at this thing here. So what I need to do here is that I need to start to interpret the meaning of work. Okay? And what we're going to find here is that the way we do this is we write down the first super important theorem of the chapter, which is called the work energy theorem.